Welcome to our today's tutorial on Arcgis. In our today's tutorial, we will be creating topography raster from coordinates and elevation, that is XYZ value, and from that value when we create a topographic layer we will use interpolation method, and in interpolation we will choose IWD formula, and then from the digital elevation model and from our given flood level we will determine in a city which area will be flooded and which area will not. Here you can see I have an Excel file in where you can see the first column is ID, then point X, point Y and point Z. Point X and Y are saying the coordinates of the place, and of that place point Z is telling us what is the elevation, and that is in respect to mean sea level. Okay, you can see there is a lots of data. There is 4,810 data in here, so we have to export this into Arcgis. But as you know, in order to do so, what you have to do is you have to select the portion of your Excel file. Okay, so when you have selected, you give here a name like just your name and then press enter, and this area in here will be called by this name you give. Okay, then go to ArcMap and then import this data. Okay, I'm going to my folder, and then remember in ArcMap you better work with XLS file, not the latest version which is XLSX, because in ArcMap it works better with the previous generation of Excel file. Okay, double click in it and then you can see there is my name and then add the file. So nothing will be shown in here because you have to right click in here and then you have to press display XY data, and in X field obviously point X, in Y field obviously point Y, and in Z field obviously this is point Z. And you can see in the description it's saying unknown coordinate system. We have to define coordinate system in order to work smoothly. So go to edit, and as this is a data of my country, and in my country the default projection system is BTM, so I am selecting BTM, and this data were also collected in BTM. So when you are working with other file, make sure you are giving this projection system which was in the file. Okay, then press OK and again OK, and there is a lot of IDs, so there will be a pop-up, just press OK. So these are my data, and what I have to do now is I have to create a raster surface from this data. Okay, then go to Arc toolbox, then go to 3D analyst tool, then go to raster interpolation and in IDW. So in IDW my input feature is obviously the events, and remember there will be an Z value field, give point Z as its Z value field, obviously point Z, and then determine a location for your output raster. This is very important. Give a name like IDW and then save, and output cell size, just write it 300, and that is why because later we will deal with a DEM file which will be pre-given, and the raster cell size of that file is 300, so in here we will also give 300. Okay, then search radius is variable, number of points is 12, maximum distance you don't need to work with this, there is input barrier polyline feature. This is if there is a some types of barrier, then you have to do this. If not, then you don't need to do this. Okay, as you can see, this is my topographic layer, which is in raster surface, and now I don't actually need to see the points. So as you can see, this is my data, this is the raster surface I want, this is a raster image. So now what we will do is we will do this analysis with the fault line. A fault line, what is a fault line? A fault line is some types of barrier where a river or something cannot flow through. Okay, then go to, just bring your file in faultline.shp, import this, and there is unknown spatial reference, click OK, and then go to data management tools and then projection and transformation and define projection, and the fault line is obviously same as my raster, that is BTM, then press OK. So here you can see now there is there are some fault lines in here. Okay, then I have to do this map again. So go to IDW, everything is same as before, ID is point Z, the output raster, this time IDW fault. Okay, and then the output raster cell size is 300, and now in input barrier polyline features, which is the fault line, then select the fault line. Okay, so I'll press OK now, and then this process will take quite a bit time, so just wait for a while and let it finish. So you can see my task is finished, it's showing the completed icon. It took almost 35 minutes. So now what we need to see is we need to see the changes it has made. So if we, in some place, if we, you can see from the layer, if we show it and if we hide it, you can see the change. And to see the change more perfectly, go to Windows and then image analysis. In image analysis you will given some options and select on the top one, and then what you do, select this icon in here. So when you select this icon, then you can see there you are given some types of cursor, and when you drag this cursor over the image, you can see the change it has made. See, there is a massive change in the place, you can see in the height. So this is our image analysis. So now let's come to our next part, which is calculating the dam and determining the flood level. So I will add my data, which is in dam. As you can see, I have two data, which one of them is meter and one of them is millimeter. So I will bring the millimeter one. I will show you something which is conversion from meter to millimeter. Go to arc toolbox. So from the arc toolbox you can go to spatial analysis tool and then there is map algebra, and then there is the raster calculator. In short form, you can just search in ArcMap, then there will show you that. Okay, so I have DEM BGD V1M layer in here. So double clicking on this one, and as we are converting it from meter to millimeter, we will obviously multiply it with 1000. But there is a small problem, which is in raster calculator, if you just normally multiply it, then you will lose precision in a great amount. So what you will have to do is you have to choose float from here. Okay, in math, under math, you will find float, and inside float double click on this one, and then you multiply it with 1000. There, then you will get it in millimeter version, but I don't need it right now, so I'm not doing it. Okay, cancelling it. So as you can see, my DEM of water heights, this is just this area in here, but the rest of the area is unnecessary, really unnecessary to me. So what if I just expect my raster image to be just of this size? Okay, so in order to do that, just before that, you can see there is too many float line in here, and this much float line cause a really great time to compute, and so we'll keep just one fault line just to show you how we do this. Okay, go to fault line and go to definition query, and then go to query builder, and then if id get unique values, and then just keep anyone. Just in here I'm just keeping only number 27. Okay, so where is my fault line? In this area. I shouldn't take this one. Okay, I'm changing it, like taking 32. Okay, where is the 32? In here. So this is my only one fault line. So now if we want to do the work, only one fault line will be counted. Okay, let's go to the IDW tool, which is under 3D analyst and raster interpolation. So click on IDW, and the previous things are just like before. The events z value is point z, and output raster, this one with fault line and also with compacted. Okay, then save it, and output raster cell size is 300, as my DEM value cell size is 300. I will show you. Okay, then my input polyline features is obviously fault line, and now if we want to make our area common just on under the DEM level, then go to environments. Under environments, you are given a lot of options, and workspace, your current workspace is, just keep it default. Then output coordinates, no. Processing extent, so this is where I have to modify. Go to snap raster and select the one you want to keep, which is DEM BGDVM, and the extent is, okay, the snap raster is extent is default, and the snap raster is DEM, just and then in raster analysis, under raster analysis you will be given a option mask. So go to mask and select again the DEM BGDV. So under raster analysis, the cell size will be same as DEM. Okay, then press. As you can see, my IDW with the masked layer is now been creating. So finally, after a lot of struggle, we have got our IDW of only the portion DE, our DEM. As you can see, this is my DEM and this is my IDW. So now what I need to see the area where they intersects, or in which places the IDW is higher than DEM or the DEM is higher than IDW. So in order to do that, we will use our raster calculator, which is under spatial analysis tool and map algebra. Go to raster calculator. So as you can see, two layers is already given. So what we will need, we will first select IDW, then we will minus the DEM from it. Okay, and our output raster, this is, suppose this is our flood level, so this is flood level. Save it and then press OK. Something has been computed. So this has been created and this is our flood level. So I am hiding everything else, everything. If this is really the river, then to check it, we'll bring our river shape file, which is in shape, and this is river shape. Okay, bringing my river shape. As you can see, the river perfectly coincidence. As you can see, the blank spaces are now filled with the river. And I will also change my color RAM. This looks a bit ugly. Okay, as you can see, now from this image I can tell which area are what, which area is below the mean sea level and which area is of how much height. Now what we'll need to do is we need to reclassify this data. I have 0 to 0.3 which is flood free area, and up to 0.9 which is flood level 1, up to 1.82, 3.63, and more than 3.6 meter is 4, flood level 4. So now let's go back to our arc map, and now what we need to do is we need to reclassify this data. To reclassify our data, we have to go to our toolbox, and under spatial analysis tool, now we need to go to reclass, and there is the option reclassify. Okay, what is my input raster? My input raster is my flood level, and the reclass field will be obviously value, and then go to classify. Okay, so the method we will keep it in not natural breaks. I will change to classes. As we have seen, we have how much classes we have? We have 5 classes, so I will need 5 class, and let's go to from top to bottom. So this was more than 3.6, so let's make it up to 10, and this one 3.6, this one is 1.8, and this one is 0.9, and this one is 0.3. okay, then that's it, then we press OK. So this is our will be our reclassified data. So let's also save it, a flood reclass. Okay, then save it, and nothing to do it from here, so press OK. So now you can see which area is in which zone. So this is actually very helpful for us to see which area is under which zone, which area belongs to which zone, which area is flood free. Our the number 1 in here, this area is completely flood free, and area 5 is very much flood risky. Now we also have to rename this data. So go to properties and symbology, and I will change the label. This is flood free zone, so this is FF, this is F flood level 1, flood level 2, flood level 3, and flood level 4. Then we press OK. So our name is now also changed. Symbology, we can give it a pretty color, which is just changing the color scheme. So I'm changing it to OK. So this is our data, and now we can see the only 3D version, as this is there is some high level and low level elevation. So if there is some 3-dimensional viewing, so this will be very helpful. In order to do that, go to Arcscene, which is under your Arcgis, and then go to Arcscene, and then go back to your arc map. And what was our final edition? Our final one was flood, this one. So right click on it and copy it and return to Arcscene, and under scene layers paste layers. Okay, now we have pasted it in our Arcscene. As you can see, you can rotate it like a 3D, but it is not 3D yet because we have not made it 3D. Right click on your flood, and then go to properties, and there will be an option which is base heights, but there is no elevation value from a surface selected. So select floating on a custom surface. Okay, my custom surface is selected, the raster resolution is default, and then you press OK. So now there is some change, but you can see because the change is very low. As you can see, this is a very big area, so in order to see the little change, you will need to zoom in very much. So in order to see it visually, go to scene layers and right click on it, scene properties, and in vertical exaggeration you enter any value, like I am pressing 300 and click OK. Now you can see there is now some height. You can see there are some height. The dark blue ones are very high in area, and the white one are the lowest. In order to make it more visible, you can always increase the value. So suppose I'm giving 800, and then press OK. As you can see, now it is very much visible. The whole surface is now something. This is something. So suppose in my map the darkest one are in above, this is high, but if you need the darkest one to be low, so go to scene properties and just in case of 800 add -800, and then you can see now the darker places are below and the white levels are up. So now you have an idea how this works. So let's go back to our arc map, and then we will do our last thing today, which is zonal statistics. So to do zonal statistics under special analysis tool, go to zonal and select zonal statistics as table. So my input feature will be flood, and also my input value will be also flood, and my output table will be zone. I think there is another file. Okay, then press OK. So now we have got a table which is like this. So now you can see we have something like in under for which value what is the minimum and maximum value. What we will do is we will also add another file which is Thana boundary. I'm adding this Thana boundary as my layer, and we will do the zonal statistics again. And in this case our input value will be flood RC and input raster will be Thana boundary, and the zone field will be Thana name, and my output feature will be zone Thana. Then press OK, and now we will get a table like this. So this one is efficient. The previous one was not really good because there was no meaning of anything. So as you can see, for my thanas here, these are the thanas. For which thana, what is the count and what is the area, in which area belongs to which place. So this is how you can do flood calculation in ArcGIS. Thank you for today.